So reviewing how to solve a differential equation. Remember, your goal on these is to get all the x's on one side and all the y's on the other. So what we usually used as a strategy was we cross multiplied. That would at least allow us to level everything out. So if I cross multiply here, taking this first diagonal, I've got dy times x squared. That's x squared dy. Equals on the second diagonal, I'd have y to the fifth times that quantity of 3x plus 2 times the dx differential. Did not quite achieve my goal of getting the x's on one side and the y's on the other, so we got to do some rearranging here. I think what I'm going to do is I'm going to start by moving the y's to one side. So I'm going to take this y to the fifth, I'm going to divide it over. By doing that, that allows me to cancel out the y to the fifth from the right side, isolating at least some of the x stuff. And the y comes over to the left side, at least joins that dy notation. Now as I divide this over, and we talked about this too, when we're dividing we know about the negative exponents, right? So we shift that up, we make that a y to the negative fifth dy. At the same time you've got this x squared hanging out. What remains on the right side, you've got the quantity of 3x plus 2 and dx. So now that leaves us with that x squared we don't want on the left side. We want to move that to the right, so divide both sides by x squared. If you do that, x squareds cancel. You've got the y to the negative fifth dy equals, dividing by x to the second, same thing as bringing that x to the second up, making that x to the negative second, times that quantity of 3x plus 2 dx. And now that I've separated my x's and my y's, I can anti-differentiate each side. And really before I do that, it probably makes sense, since we know we'd have to multiply through anyway when we take the antiderivative, it makes sense to distribute that x to the negative second through. So as I distribute that x to the negative second through, you've got 3, since that's an x to the first, adding your exponents, it'd be 3 plus the negative 2, so negative 1. Negative 1 would be the new power. Plus x to the negative second times 2, got 2x to the negative second. So I've got those terms with the dx. Left side stays the same. And like I said before, since you got the y's separated from the x's, you can take the antiderivative now of each side. So bring that up here. Taking the antiderivative on the left, you're adding 1 to that power of negative 5. You've got y to the negative fourth. Take that reciprocal of negative 4 being negative 1/4. Bring that to the front. That equals, okay, this x to the negative first. Remember, that's a special one. Anytime you see a negative first as a power, you got to think natural logs. So it's 3, because of the 3 in front of the x to the negative first. It's 3 natural log of the absolute value of x.
How did you get the natural log thing?
Okay, on the 2x to the negative second term, we're adding a power there, a value of 1. We've got negative 1 as our new power. Reciprocal of negative 1, obviously negative 1. Bring that to the 2 in front, makes that 2 negative. And because this is not a definite integral that we're applying to each side, remember you need the plus c. Now at this point, it could make some sense to try to clear the fraction out. I'll be honest with you, given the details of this problem, if you get this far, I'd say we're doing pretty well. So we'll accept that as our answer. All right, so another differential equation we got to solve. If the little cross multiplication trick works for you guys, we could use that again here if we just place this side over 1. Cross multiplying, You've got your dy times 1 for the first diagonal, so dy on the left equals, for the second diagonal, it'd be 7. And as long as I'm at it here, it's the cube root of x squared, right? So if I rewrite that with a rational exponent, it would be x to the 2/3. Right? The cube root gives me the 1/3 part. Because of this extra power of 2, we just make that the numerator on the rational exponent. So I've rewritten that, still multiplying through on that diagonal, got dx. Your goal is to get the x's on one side and the y's on the other. This one's really nice. We've accomplished that. So once we've achieved that goal, we anti-differentiate each side. On the left side, we don't see a little function here, but it's understood that there's a 1 there, right? So if you take the antiderivative of any constant, the rule is attach an x, so that would be a 1x. In this case, it'd be y, though, because we're taking the antiderivative with respect to y. On the right side, if you add 1 to your power, you've got x to the 5/3, reciprocal of which is 3/5. The 3/5 gets multiplied to the 7 in front. That would be 21/5. 3/5 times 7/1, right? And have to add on the c, since we're done taking the antiderivative there. And really no reason to clear the fraction on this one, because this one's in a nice clean function form. Y is set equal to everything else, so I wouldn't mess with that answer. All right, so here's the long and short of this problem. We're trying to take this idea that's set up for a Riemann sum, and we're supposed to express it as a definite integral, which would be a Riemann integral. When you think back to how you found problems using a limit of a Riemann sum, there was this little setup where we had f of, it was a plus I delta x, all of that times delta x. And then we had our limit and our sigma notation applied to that. So when we're trying to go backwards here and set up the Riemann integral that would basically give us this form, the key was looking for any I over n stuff in the original Riemann sum. So notice I have an I over n right there. Once you locate where the I over n stuff is, take anything that's attached to it as a quantity, make that your x. Okay, make that your x in the original function. If that's my x, then down here, as I apply my integral, I need to apply it to some function. I'd have x raised to a power of 2, because that entire quantity is raised to a power of 2. And then we added on this 3 to complete the function. So you locate the I over n stuff. That gives you the x to start with. Then anything else that's applied to that x, the squared in this case, the plus 3 in this case, that makes up the rest of the function.
What about the -1 added?
All right, so you get the function first. After you get the function, then you need to figure out your interval, because you need some values over here to complete the definite integral. To figure out those values, that's where we go back to this I over n stuff, and we look to see what's added onto it, subtracted onto it. In this case, when we go back to that I over n stuff, we've got a -1 that's added on. The -1 tells me where the interval begins. So -1 starts there. And now, as you consider, you could look at the I over n stuff, you could look at anything else over n, you'll notice that you've got a 5 on top wherever you look at these ratios that have n as a denominator. That 5 makes up the difference between this number and whatever's on top. So basically, I find this number, and then I take the top number of 5 in this case, I add it on. That gives me the 4 up there. To complete the process, I put a dx at the end to make this all official. But this would be my Riemann integral, or my definite integral, where if I had to evaluate it using a limit of a Riemann sum, eventually I would get back up here. All right, Alright, so we're supposed to find the exact area here of this function, the x-axis. It's not a problem for us now. After all, we understand what these antiderivatives, all these integrals that we've been setting up, all these definite integrals that we've been setting up, those are supposed to give us the exact area beneath these curves and above the x-axis. So what I would do here is I would set up a definite integral. I would apply that to the function that's given. The biggest problem here is we don't have an interval to work with. At least it doesn't appear that way based on the given information. But as long as you understand the visual of what's going on here, you could take this function and you could graph it out. And as we graph it out, oops, it's negative, isn't it? All right, so there's the curve. Our goal is to find the exact area basically in this region here. And to do that, we need an interval to work on. Since it's above the x-axis, we could take whatever this point is and go up to whatever this point is. So as we make sense of it from the graph, looks like we're crossing here at -2, I'm sorry, not -2, +2, and we're crossing here at +6. So my interval would be from 2 to 6. Now, if you didn't have the graphing technology here, what you could also do is you could take this function, you could set it equal to 0, and you could find your x-intercepts that way. So where was my function again? Plus 24x minus 36 equals 0. If you solve this for x, factor out the -3, at x squared minus 8x plus 12. All of that we set equal to 0. -3 is no longer relevant. We could divide that out since it doesn't have an x, but if we factor what remains, now let's see, we've got x, we've got x, we've got -6 and -2, right? So notice the solutions you get back from those two factors. From the first factor we get 6, from the second we get 2. So really two options there. You could graph it out, you could locate the intercepts that way just by looking at the picture since we understand how this visual works. Or if we don't have the graphing technology, we could factor it out. Either way, definite integral is going to be based on the interval 2 to 6. Once we establish that, this is the problem we got to evaluate. So we know to evaluate this, we take the antiderivative of each respective term. So add 1 to my power here, get 3. Reciprocal of 1/3 gets multiplied to the -3 in front, giving me -1. Add 1 to my power here, 1, I get x squared. Reciprocal is 1/2, that gets multiplied to the 24 in front. Got plus 12 now. Minus, rule is on the constant, just attach the x. Still have to acknowledge the interval we're working on. So there's my interval 2 to 6. At this point, we take our 6, we plug in for each x. So we would have -6 cubed plus 12, 6 squared, minus 36 times 6. We'd evaluate that when 6 goes in, and we would subtract. We take this 2 and plug in for every x. So we have negative be 2 cubed plus 12 times 2 squared minus 36 times 2. You calculate each part and find that difference. Turns out that the exact area is exactly 32.